Hi everyone. Sunny just covered air pollution. I'm here to talk about water pollution. So my name is Will Tarpeh. I'm in chemical engineering at Stanford. I wanted to kind of summarize the three areas my group works on. But first of all, when we think about wastewater, we think about it as a source of value. So many of us have thought about, and maybe some of you have checked the COVID-19 tracking in wastewater to get a sense of how high levels are. That's one of the instances of the value we can get from wastewater in terms of information. Turns out there are lots of other pollutants in wastewater that we can actually turn into commodity chemicals or valuable products. Think fertilizers, disinfectants, other things that are manufactured chemically. So we can sort of solve two problems at once: remediate pollution and make something valuable, hopefully while reducing the environmental impacts of chemical manufacturing. So the methods my group uses to do this are really threefold. First, we focus on selective materials. So think about a Brita filter and the beads within it, designing new versions of those that are highly selective, so you can extract just one type of pollutant, like ammonia or nitrate, from a very complex wastewater. Second, we use electrochemistry as a driving force. So we design reactors and look at a molecular scale in terms of using electrons as a driving force for reactions and also for separations. And third, we do some of this scale up of some of these reactors and some evaluation of these in terms of life cycle assessment and techno-economic assessment, so that we can try to see what the impact is of some of this work, especially with respect to global sanitation and to reducing the health burdens from some of these pollutants. So I want to just give a couple snapshots on the materials side of the group and also on the electrochemical side. So this is actually collaborative work with Laura, who was our first speaker in this session, and a couple other colleagues at Stanford. But we're looking at ammonia transporter proteins that have been isolated from E. coli and from other bacteria. And we're actually attaching them to, back to that Brita filter analogy, to basically new types of adsorbent beads, so that we can achieve highly selective removal and recovery purification of ammonia from really any wastewater. And so how we do this is construct vesicles, load these vesicles with some of these AMTB ammonia transporters that are much more selective than me as a polymer chemist I can make, and then we try to characterize their separation performance by immobilizing these proteoliposomes onto adsorbent beads. We've also done this in a membrane fashion, so you can think about a flow-through pattern rather than just an on-off switch. And then we can use this to actually characterize some of the transport and the selectivity of the transport in some fundamental ways. In terms of the electrochemistry, we try to use these electrons, like I mentioned, across multiple scales. So on the top left here, we think a lot about what we call the microenvironment and the real wastewater effects. So here, there can be many different cations, anions, organic compounds in wastewater that can interfere with our electrode, shown in gray, and really drive some of our reactions and the observed selectivity. Then we design these new processes and try to focus on how can we control the composition using membranes and when we apply the potential. And then we think about, as chemical engineers, how do we put this in a treatment train of different wastewater treatment processes? What goes before and after? So one of the things we're really excited about is being able to oxidize and reduce nitrogen kind of at will here from two different ways. Ammonia and nitrate are both different pollutants in wastewater. They cause eutrophication. So many of us saw the big algal bloom that happened in the San Francisco Bay this summer. Turns out that happens a lot everywhere around the world. And ammonia and nitrate are the major culprits. And then the last thing to show here is that we can do this repeatably from real wastewaters and get more than 90% of recovery on a repeatable way. So thank you very much, and looking forward to chatting more.